using the area product approach for designing the magnetics, both inductor and the transformer. So let us look at what area product means. So there are two important areas for any core. One is the core cross section area AC in meter square. Core cross section area. What is the core cross section area? You see this part here, the central, this is the E core. You have seen this E core, I have shown it to you before. On the extreme sides there are thin limbs, and on the inner, the central arm is the thicker one. So this area here, which I am showing with a pencil, is the core cross section area, and perpendicular to that, orthogonal to that, there will be flux flow. Next, let us see another area called the window area. Window area symbol is AW meter square. And what is the window area? In the case of the E core, you see there is this one E core. I will take the other one and place it on top of this like this. This will be the completed E core, as you see it here. Now this gap here, what you see here is the window area. This area here is window area. Not both together, any one of the area only. Either it is this area we have to take or that, because a turn entering here will also come out there. So it is only one area that we need to consider. So this is the window area. So that is what we call as window area. And now area product AP is AW into AC or AC into AW, and this is meter to the power of 4. Now AC into AW is called the area product. When we do the core design for inductors and transformers, we will be calculating this area product AP and checking against the table of cores for the area product that matches or is greater than the value calculated, and we will select such a core which has a greater datasheet value AP than what we have calculated, and then use it for design. This is an iteration process. Of course, we will now discuss how we will use this area product to design the cores for the inductors and the transformers. Now consider a core. Let us take an E core, and we saw just now how the window area looks like. This is the window area, and this is where you will see the cross section of the wire. So first let me draw the former. You will have to place the former. There will be a former section which is going to come in here. It will eat up some portion of the window area. This is the former section. Then let us say we put in the turns. So these are the wire cross section. So this is one single turn. The cross section will appear on this side of the window area and also on this side of the window area. So I will just put one layer. There may be many layers which will fill up this entire window area. So this is an E core. Now this portion here which I am showing marking on the with the cursor is the window area. So this is the window area EAW. However, you should understand that the entire window area is not available for you to fill it up with windings. So there is some loss in the available window area. What is the loss? One is we just saw that there is this coil former which is eating away a portion of the area. Then when you are winding, the cross section of the copper wire is circular in nature, and there will be air gaps in between the windings. So that is going to take away some window area. Thirdly, the cross section of the wire has enamel covering on top of the copper, so that there is insulation between the windings, so that there is no short across the windings. So this enamel over copper. So if this is the copper cross section wire, over that there is the enamel, such that there is an insulation between two neighboring coils. There will not be a short circuit. But this enamel cover is going to eat up some portion of the window area. So now all these are going to reduce the window area by a factor called the window factor Kw. So this window factor Kw has a value less than 1, and the available window area can be written as Kw Aw. And for the inductor, Kw is between 0.4 to 0.6. So to understand that it is not easy to deterministically evaluate all these loss and available window area, because many a times the air gap between the windings depends on the skill with which one winds. So therefore we have a range of Kw. So if someone is a novice who is winding it for the first time, who is a newbie, the Kw factor will be lower, and someone who is very experienced and has very good skills in winding the coils will be around 0.6 Kw. So now I have shaded one wire cross section. So that area which is shown black is called AW's lowercase w, which is the wire cross section area. It is the cross section area of the copper wire. It is only of the cross section area of the copper wire inside, not excluding the enamel, because the enamel portion is taken within Kw. So if there are n such turns, n such cross sections will be there. So Kw Aw should be equal to n into area of cross section of the wire. Now area of cross section of the wire, we will write it as IRMS. There is a RMS current that flows through the cross section of the wire and a permissible current density. So there is a permissible current density J, and this for copper is at a default value of around 3 amp per mm square, or 3 into 10 to the power of 6 amp per meter square. So this is in amps, this is amp per meter square, and therefore the units of kWAW will become meter square. So this is the starting value, the default value. The J varies in practice from 2 amp per mm square to even 5 amp per mm square in very low power systems. As the systems become higher and higher in power, the J value becomes 2 amp per mm square. 3 amp per mm square is a reasonable value to take for most of our design purposes. Let me represent the RMS current here in terms of max current. So let me introduce the term crest factor. Crest factor is Kc, which is I max or I peak divided by I RMS. And therefore, using this relation here, you have kWAW equals n times Im by crest factor into J. Or Im can be written as kW AW Kc J divided by n number of turns. So this is a nice relationship. We'll mark it as 1. The current, the max current through the inductor is expressed in terms of the number of turns, the window area, the window factor, and the current density J. Next, we go back to Faraday's law. The voltage across the coil induced is equal to L di by dt, which is also is equal to N d phi by dt. Now phi can be written as AC into B. AC is a constant, so N AC dB by dt. So consider these two. If the voltage is constant, the rate of rise of the current is linear. Therefore, rate of rise of the flux density should also be linear. In a given time, let us say the current rises to Im, from 0 to Im, Lim. And at same time, the flux density would have reached Bm. So N AC Bm. So this is another relationship where Lim, the current, is related to the magnetic properties and the core cross-section area. So this is relation 2. Now let us evaluate the energy stored in the inductor. So what is the maximum energy stored in the inductor? Half L Im square, max current square. So this I can write it as half L Im. I will group this together into Im. And we have developed relations for Lim, wherein Lim is related to AC, and we have also a relation for Im which is related to AW. We will substitute these two relations here and rewrite. So Lim, I am writing it as NAC Bm, and then for Im here Kw, Aw, Kc, J by N. So let us remove these two N's, and I will keep AC and Aw to one side, their product. This is the area product, AC into Aw, which is equal to 2 times EL divided by Kw, Kc, J and Bm. So this is area product AP, meter to the power of 4, and this is the area product equation, and this is the equation that you will be calculating and checking it in a table of cores and comparing it with the area products of the cores, and you will pick out that core which is having an area product greater than that which is calculated, and that is what we will be using for the inductor design and later on for the transformer design too. But for the transformer design, the area product equation will be different. We will come to that later at that point in time.